In this video, I'm going to use a couple of table of values to illustrate horizontal translations. Here's a quick summary that you're probably familiar with, showing the function notation necessary to move a graph up, down, left, and right. And most students find the first two of the transformations very intuitive, that if you add or subtract, that would move the graph up or down. Turns out this is always the case that when you manipulate the output of a function, notice that here we're taking the y value of a point, the function value, and adding 3 to the y value, or in this case subtracting 3 to the y value, that things play out the way that most people think that they would. But whenever you're manipulating the input of the function, notice here we're adding 3 to the x value of the function, not the y, and here we're subtracting 3 on the x value, not the y, things work against your normal intuition. Adding 3 actually moves things to the left 3, and that's what we're going to explore in this video. So note so far in these tables of values, I actually never defined what the function f of x is. This is to show that the result that you'll see coming from this analysis I'm about to do is true for any function that you could dream up. So in my first cell here, I see that x is 0, and if I replace this x value in here with 0, I get the notation f of 0. This is just the notation to represent the y value of the function when x is 0. Repeating this, replacing x with 1, this would become f of 1, and then of course this would be f of 2, f of 3, f of 4, f of 5, and finally f of 6. Now let's see what happens when we add 3 to the input. Because we're changing the input values and not the output values, you should know that these two functions would have the same outputs, but they'll happen for different inputs, and that's what I'm about to show. So I'm going to repeat the process now. I noticed that for this first cell, x would be 0, so to fill out this cell, I would replace this x value right here with 0, and it would read f of the quantity 0 plus 3. And since 0 plus 3 is just 3, this becomes f of 3. So already you can see that this notation matches this notation up here. But what you want to notice is this x value that produced f of 3 is 3 in this chart, whereas here we replaced x with 0 to get the output f of 3. So we're going to get the same y value in the function, or the graph will have the same height, if you will, same y value, but it'll happen earlier on in the second function. It'll happen at x equals 0, where in the original function it happened at x equals 3. So we're going to get the same y value, but for an earlier x value. That means we'll get that y value further to the left on the graph. So already you're starting to see that this notation f of quantity x plus 3 moves things to the left. So this cell matches this cell here, and you should see that the rest of the table will line up as well if we continue the process. So for example, for this cell now, if I replace x with 1, I'm putting x equals 1 right there, and this will read f of the quantity 1 plus 3. And then since 1 plus 3 is 4, you get f of 4. So notice that the output here is f of 4, and here we have an output of f of 4. So if you compare, it used to take an x value of 4 to produce that result, but now it only requires an x value of 1 to produce that same result. And it should be obvious because we're adding 3 to the input. So since my input's 1, but we're in the business of adding 3 to it, plugging 1 into this function is equivalent to plugging x equals 4 in the original function. Plugging x equals 1 into a function where you add 3 to the input would be similar to plugging 4 into the original function because you're adding 3. So notice this output at x equals 4 matches the output here when x was 1. I'll do a couple more. In this cell here, we have x equals 2. I'm working on the cell when x is 2. Replacing x equals 2 into the function notation, that would read f of 2 plus 3. And since 2 plus 3 is 5, this would read f of 5. And we already got an f of 5 in the original chart right here. We had to plug in x equals 5 to get f of 5. Now, to get f of 5, we only need to plug in x equals 2, and again it's because we're adding 3 to the input. Plugging 2 into this function is the same as plugging 5 into this function, because the first thing you're doing with this second function is adding 3 to the input. So here we have the same output as this, but it happens 3 units to the left. Now, lining the charts up here like this and saying that things are happening 3 units to the left only makes sense because we lined the charts up both at x equals 0, but it still makes sense. But I want to show the connection between the table and a graph, since most often when we talk about a function moving to the left, we're talking about its graph, not its equation or its table of values. Okay, I'm going to fill out one more cell in this bottom chart here, and we'll compare what happens at x equals 6 as to compared what happens down here at x equals 3. So since in this cell x is 3, I will replace x with 3 in the function notation. That'll leave me with f of quantity 3 plus 3. And 3 plus 3 is 6, so I get f of 6, which again matches up with this over here. We get f of 6 in the original table when x is 6. But down here, to get that same output of f of 6, we need only replace x with 3. So we get that y value 3 units to the left, at least since we're lining these tables up. Now let me actually define a function. Suppose I decided to make f of x the function x squared. If I did that, then that would mean I take the inputs in this top row here, the x values, plug them into the function, and simply square them. So f of 0 here would be 0 squared, which is 0. F of 1 would be 1 squared, which is just 1. When x is 2, f of 2 would come out to be 2 squared, which is 4. F of 3 would be 3 squared, or 9. 4 squared is 16, 5 squared is 25, and 6 squared is 36. So if you were to look at these numbers here in the chart, that would happen over here, because this f of 3 matches this f of 3, and we just saw that f of 3 is 9. So I better write 9 here, ran out of room in my table. And you could continue on. Here we have f of 4, which is 16. So over here where we have f of 4, you would have 16. And I don't need to go any further. You get the idea. This would be 9, 16, 25, 36. You're getting the same y values, 9, 16, 25, 36, but you're going to get them for earlier x values. Instead of getting them at x equals 3 through 6, we get them for x values 0 through 3. X values that are 3 units smaller. And that makes sense. They can be 3 units smaller because I'm going to add 3 to them first thing I do when I evaluate the function. So I just want to focus on one point to make sure that what I'm saying makes sense. In this top function, if you replace x with 3, right there, you get a y value of 9. That means this graph would have the point 3 comma 9. In this function, this cell here is telling me that you only need to plug in x equals 0 to get out y equals 9, so it would have the point 0 comma 9. So if you simply just plot 3 comma 9 on a Cartesian coordinate system, label it on a graph called f of x, then plot the point 0 comma 9, but label that graph f of x plus 3, they are two different functions, you see that you get the same y value of 9, but at an earlier x value. You get it at x equals 0 instead of x equals 3. And just to quickly show this, I actually graphed f of x equals x squared and its translation on the same Cartesian coordinate system. So notice the red graph here is f of x equals x squared. If you want, you can see it right there. I told Desmos to graph y equals x squared in red. And notice on f of x you have the point 3 comma 9. When you square 3, you get 9. And then on the blue graph, the one that's been transformed to the left 3, you see that you get the same y value of 9, but for an earlier x value. So just looking at the plot 3 comma 9 and 0 comma 9, you would see points on the blue graph should be the same as the points on the red graph, except moved to the left. Getting y values for smaller x values mean that points are further to the left on the graph. So simply put, when you look at the point 3 comma 9 and compare it to the point 0 comma 9, you can see that our original function f of x has a point over here, and the transformed version f of x plus 3 is further to the left because it has an x value of 0 rather than an x value of 3.